Hey folks, welcome back to Combo Class. I'm Demotro, and this is a chart I made of how some numbers would be written in a whole variety of different bases, and I have some cool stuff to show you about it. Now, the things I want to show you in this episode are things I discovered myself, you could say, when I was playing... Oh, a squirrel. Things I discovered myself, you could say, as I was playing around with numbers, but they're simple enough of discoveries and connections that I'm sure other people have had these realizations before, and they're also simple enough that some of these things may seem obvious to you once they have a second to sink in. But some of them may also be things you've never thought about before the moment you get the chance to bring them into that part of your brain where we keep obvious things. Some of these things you may have never considered, and then all of a sudden seem like an obvious truth. And maybe those are the types of knowledge that could be most important to learn. So let me show you some things that now seem obvious to me, but I'd never thought of a few years ago. Now, to clarify about what I mean by different bases, we count in a base 10 system because numbers have symbols put in spots that symbolize powers of 10, starting from the 0th power, which is 1. But we could have counted in a different system, like a base 6 system, where we'd have 6 to the 0th powers there, 6s there, 36s there, because that's the next power of 6, or some other number from our base. And we are just going to be looking at bases that have a positive whole number 2 or greater for the base today, because those all play by the same rules and setup. And since it's going to get kind of clunky to keep saying bases that are positional and use powers of a number that's an integer 2 or greater and use the digits between 0 and 1 less than themselves, let's categorize all of that as what we'll nickname basic bases. So when I say all basic bases, I mean all these whole numbers 2 and up used in a similar way to our base 10 system. On this side of the chart, I've listed numbers from 0 through 12, just drawn as the amount of dots that would be that number of some item. And that's a more neutral or fundamental representation of the numbers compared to any of these digit strings, which depend on a particular base number to decide how it's going to be represented. And they're in different shapes, because I decided to organize the dots for any given number in as close to a square rectangle as possible while having it all be an even shape. And this already shows us some patterns related to types of numbers that you already probably know. Like prime numbers, we think of as numbers that can only be divided by 1 in themselves. But here we can see them visually as the numbers whose only rectangle looked like a line segment. And we can also spot the square numbers like 4 or 9 because their rectangle fit into a perfect square shape. And on the rest of this chart, we have representations of all these numbers in different bases. All the basic bases, as I called them, from 2 up through 12, although we could imagine this chart going infinitely in both directions to look for patterns. Now, we're used to all of the digit symbols that these first bases use, but once you get to base 11, we'll note an A there, because that's just representative of whatever symbol these bases past that point would need to use as a single digit symbol. Similarly, in a base 12, we have A and B as possible symbols that might pop up, because base 12 is going to need a single digit symbol for 10 and 11 of a thing. One thing you might notice is that the single-digit representations here are divided from the multi-digit representations by this diagonal line of what looks like tens, the 1-0 numbers in these bases. And that happens at the spots where a base tries to write down the number that's its own base number, like 3 in base 3 or 4 in base 4. And that relates to how all of these basic bases would consider themselves in their own language to be base 1-0, what looks like base 10 to us, but in their own language would mean base whatever number the base is. Like in base 4, to say base 4 written down, it would look like base that, 1-0. So when I write down base 10, I sometimes like to spell out the 10, base T-E-N. Otherwise, it's arguably ambiguous which base I'm talking about. And we need some sort of neutral standpoint to come from. It's hard to use these dots as a neutral standpoint when you get to bigger numbers. And when we describe other things, like base 6 or base 12 or something, we just go with writing them as how that amount would look in this base 10 column. But I think it would be more fundamental to start lower and name the bases after what they would look like for their base number in the first of these basic bases, binary. And if we were to describe base numbers in binary terms, well, our base would no longer look like base 1-0, but funny enough, it would look like base 1010, sort of like a doubled up 10. So maybe we should start calling base 10 base 1010 when we write it down. Now, sometimes in combo class, we've taken particular bases and looked through its list of representations of numbers. But what if we go the other direction on this chart, on rows instead of columns, picking a specific number and looking at the whole infinite list of ways it would be represented in these basic bases? Well, although it's an infinite list of representations, it hits a certain point where they're all the same. Like 5 as a number will be written as this 5 symbol in all bases greater than 5. Or 11 as a number will be written as something that I called B here that represents 11 as a single digit character in all further bases. So if we asked for the list of different or distinct representations for a particular number, it would be finite, and the amount of them in these basic bases would be equal to the number. Like 4 has 4 representations in these basic bases if we don't count all the duplicates after that. Or 11 has 11 different representations, not counting all the future duplicates. So what can we learn or know about a given number based on its finite list of representations in the basic bases? Well, if we wondered for a given number, how many bases does it look like 10 in, look like 1-0? That would be nothing for 0 and 1, and exactly 1 base for all the others. But what if we asked a similar but more general question, which is for a given number, how many bases does its representation just end in a 0? Here on this bonus column, I'm going to tally up for each of these numbers how many of its representations end in the digit 0. And we'll allow multiple zeros. It just needs to have the last digit be a 0. Well, the number 0 has a 0 at the end, technically, in its representation in every basic base. So I'll put an infinity symbol there. But let's mostly leave 0 to the side to look at the rest. 1 doesn't have that property true in any of the basic bases, and never will, so it gets a 0 there. 2 does have a 0 at the end in base 2, in that time where it looks like 1-0, But in no future bases will it have a 0 at the end. It'll just look like a single-digit 2 symbol. So that gets a 1. And 3 similarly has exactly one base that it ends in a 0 in. But 4 has not only the case of 1, 0 in its own base, but also looks like 1, 0, 0 in base 2. So it has 2 representations that end in a 0. Now let me fill in the rest of these. So what can this list tell us? Well, if we look at the numbers that only had one representation ending in a 0, you'll notice those are the numbers that look like line segments here, the prime numbers. Prime numbers, I realized, could be redefined in a surreal way as the numbers that end in a 0 in exactly one of these basic bases. And why is that? It's because if there was another place where a representation ended in 0, that meant that there was some amount of the multiple of whatever that base number was without any remainder left over to add. And so anytime we see a representation for a number that ends in a 0, that base that represented it that way must be a factor of the number to not have any extra remainder after having some quantities of that number. And it's true that this list of how many representations ended in a 0 for each number is exactly one less than the list I could have made of how many positive factors each number has. Apart from primes, another thing this list could tell us about is sort of the opposite of primes, the type of number we've seen on this channel called highly composite numbers that have more factors than any smaller whole number. Well, if we made a list here by taking the number 1 to start and then writing down only numbers that had a record-breaking amount of zeros and representations, well, that list would be the same list of numbers as the highly composite numbers. And another way we could turn this into a type of number that you've definitely heard about before is that square numbers, the numbers that are the perfect square of another whole number, are precisely the numbers with an odd number of divisors. And since these on this list are all exactly one less than how many factors or divisors the number has, in this case, perfect squares will be precisely the numbers with an even amount of representations with zeros. Like the even numbers on this list, not counting this debatable infinity, are 0, 2, 2. Those land at 1, 4, and 9, the square numbers that fit on this list. And speaking of square numbers, that leads us to another thing about a table like this that may seem very obvious when I tell you, but maybe some of you have never thought about before. We can identify square numbers bigger than 1 on this list very easily, because those are going to be exactly the numbers that have some representation somewhere that looks like the number 100 to us. A representation written 100, like there for 4, or like there for 9. And we'd get another 100 in a representation on the next square number, 16. And if you think about the definition of these basic bases, where that spot in a number represents how many of the 0th power of the base we have, and first power and second power, it makes complete sense that having 1 of the second power's spot and then zeros for the other spots would be the numbers that are a perfect square of some base number. And since our bases started at 2, 1 got left behind again. But for all square numbers bigger than 1, we can see, of course, they have to be the numbers that look like 1, 0, 0 in some base. But it is something we sort of take for granted, that an alternate definition of square numbers bigger than 1 is the numbers that look like 100 in a basic base. And what about the numbers that look like 1,000? Well, the only one of those that fit on this list is right there, the number 8 in base 2, and that's because 8 is 2 cubed. It's a perfect cube number. And similar to the squares, if and only if a number is a cube number larger than 1, it will have a representation in some basic base that looks like 1,000 to us, 1000. And onward from there, we could note that any perfect power, the type of numbers that are normally defined as being able to be represented as some whole number A to some other whole number that's at least 2, B, well, these perfect powers in general that include squares and cubes and fourth powers and onward can also be described as the numbers that in some basic base have a representation that is 1 and then at least 2 zeros onward from there, with all of the rest of the digits in it just zeros after the 1. That does leave behind the number 1, and some people consider 0 a perfect power, many don't. But if we wanted to include 1, we could. We could note that all of the bases beyond there had exactly 1 spot where they looked like 1, 0, and some of them had a spot that looked like a 1 with multiple zeros after it. Well, we could say that the perfect powers, including 1, are the numbers that in more than one base have a representation that's just the digit 1, and then if there are any more digits, all of the rest are zeros. Some numbers can even have this perfect power trait twice. Like 16 is a perfect power in 2 ways, because it's 2 to the 4th power and also 4 to the 2nd power. And so in base 2, it would look like 1 with 4 zeros, and in base 4, it would look like 1 with 2 zeros. So if this chart went down to 16, we would know that it's a perfect power in 2 ways by seeing that type of string twice in its row. And then there's some numbers that don't have any representation that's just 1 followed by multiple zeros, but do have some representation that has multiple zeros at the end. And that type of number isn't a perfect power itself, but is divisible by some perfect power. If a number has a representation with 2 zeros at the end somewhere on its list, that number must be divisible by some square number. And if a number had a representation with 3 zeros at the end, that number must be divisible by some cube, and so on. Now, a lot of this episode was about which numbers end in the digit 0 in some of their representations, but what if we wondered about other last digits? Like, what patterns emerge when the last digit of a representation is a 1 or a 2 or something else? Are there patterns that primes or square numbers have relating to other last digits? And all of that is basically the same as the modular arithmetic patterns I've shown in earlier episodes, and more that I'll show in the future. Modular arithmetic, for those who don't know, being this awesome way of interpreting numbers like a clock that works very similarly to the last digit a number would have in a given base. And that's about all of our basic investigations for today, but I do have something else cool to show those of you who didn't see on my other channel, which was called the Combo Class Bonus channel, but now is called the Demotro from Combo Class channel, because it outgrew the bonus status. It's actually more subscribers than here. Well, to those who didn't see my announcement on there, I recently got a fun thing for anyone interested. These keys are for a personal mailbox I bought for a year that's not my home address, a different address, so that people like you could mail me old clocks, dice, calculators, or other things that you want to see in the background of the classroom during the upcoming grade -2. There's more info about that in this video description, as well as cool links to the Combo Class Discord and subreddit and Patreon pages you should check out. And we're almost at the end of grade -1. I'll see you soon for the third last episode of the grade.